Okay, let's see how this all goes together, start to finish, all the way through the selection of a beam, at least in a conceptual way. We're going to go to review here, go to start inking. Let's say you have some reason why you need to build a structure that looks something like this. And you need to put a force out here, P. All right. What do you need to do? Well, you need to do a number of things. You need to know that this beam is big enough, and you know that this is big enough, and you need to know that this is big enough. So I'm going to call this A. I'll call this B, C, and D. So you need to know the section of A. You need to know the cross section. You need the section of A, section of B, section of D, and the section of C and D. Section, you need to know the material. However, you also need to know the link, if you would, at basically, I guess, the joint at CB, I guess I'll call it, and the joint at DC, because you've got some change in the direction of stress. You need to know any number of things. Well, what do you need to know first? You need to know all the forces and all the structure, and you start that by solving for the reactions. So once again, solve for reactions. And how do we do that? Remember, we set our coordinate system there. We write 2, 0, 0, 1, 0, 0, 0, 0, 1. We do that for each of our reaction forces. We write, I'll call that 20. I'll call that distance here 20 long. That means that this is at 20 and 0, and it's at 0 and 1. This gets an asterisk. This gets an asterisk. This gets an asterisk. You have P here. P is also there at a location. Now I guess I'll call that 15 and 5 in the air, and I'll go at 0, and it's a minus P. You solve for the reactions for each of these based on reacting to P. And so you know that this here, this moment is going to generate 20 kip feet or pound feet based on it being a unit force. What is this going to generate? Well, this one's going to generate minus 15p. And so what you're going to do is you're going to have a reaction here that's the ratio of minus 15p over 20. In other words, it should be a little bit longer. It should be a little bit less than p because it's farther away. All right, once you've done that, you then just need to go to any point you want to solve the forces for. So if you go back to here, of course you have to go back now to here and calculate, change this asterisk here and this asterisk and this asterisk. And once you change them all, you now can once again go ahead and pick any point in the structure. Once you do, you're going to figure out the maximum, section A, the maximum moment, shear, and axial force P for each of these. 1, 2, 3, 4. And you're also going to look at what is the distribution of through the joints. Now, in the textbook, you'll see this laid out someplace like this. And this is actually where some of your homework is kind of laid out. I ask you some very simple questions. So let's draw 3 free body diagrams now. We're going to show this as reach D with force P, and right here we've got on it what a reaction of C onto D, moment of reaction is C onto D, and then also a shear force of C onto D. And now when we look at member C, we've got 2 of them on. We've got a reaction of D onto C, the moment of reaction on D onto C, plus the force of D onto C. And down here we have as well, we have a sets of moments and reactions. And then for the last piece, here we've got basically a force here, a force there, a force there. Then we also have a force, and a moment. And so very often you'll see that you'll be going around the structure looking at each of these individually. However, realize that once you've got these matrices and the asterisks removed, you can calculate the internal shear, axial force, and bending for any point looking forward or back, and what you have to know is the two sides should be equal and opposite. All right, so in that, once you get your maximum M, your maximum shear, and your maximum P, you go into the formula. M over S should be less than or equal to 60% of the yield strength. P over A should be less than or equal to some K, some constant, times the yield strength. This, of course, this constant is a function of KL over R, which gets even more complicated when you get a structure like this. And finally, V over A should be less than or equal to 40%. In all reality, these add together and you've got some, you're not allowed to have maximum bending, maximum shear, and maximum axial force on a structure. So there are some kind of coefficients ones used to add those two together. So that's the general process that you go to, realizing that you need to solve for the reactions first. So let me once again lay that out there, and then realizing this translating a vector, shifting your translation vector from there to there, should make the rest of this very straightforward and make it so you can prove competency. So here we go. Right? Solve for reactions, probably using matrix notation. And then you can also check or guess using vectors. And of course you'll see in something I'll link into this video, they are the same. Alright, I'm going to push this out and then link it up then to a discussion of matrices that Sal Khan does. It's about 15 minutes, and that'll be a requirement for some of you that need to be making up for not having done or handed in homework. Thanks for listening.